Welcome to Brain Vision.
Okay, so for this problem, we are asked to find the energy of a photon, an electron, and an alpha particle given its particle wavelength of 0.2 nanometers. So what we'll need for this problem, for our constants, we will need the mass of an electron, which is 9.1 times 10 to the negative 31 kilograms. And we're given the mass of an alpha particle, which is 6.64 times 10 to the negative 27 kilograms. We're also going to need Planck's constant and the speed of light, h and c. For our equations, the energy of a photon, a particle with no mass, is hc over lambda. For the energy for a particle with mass is something a little bit more complex, but not much more. It's h squared over 2m lambda squared. So these are the two equations we'll need. Let's jump into it. Okay, for the first part, we need to get the energy of a photon. E is equal to hc over lambda. We can use Planck's constant in electron volts form, 4.136 e to the negative 15 electron volts per second, well, electron volts seconds, multiplied by the speed of light, 3e to the 8 meters per second. And plugging in 0.2 e to the negative 9 meters for our wavelength, we will end up with a result of 6.2 kilo electron volts, or keVs. For the second part, we're actually considering a particle with mass, an electron. So we have E equals h squared over 2m lambda squared. Using the same h in joules this time. So 6.626 e to the negative 34 joules seconds instead of electron volt seconds. And using the mass of an electron, 9.1 e to the negative 31 kilograms. And the wavelength as before, 0.2 e to the negative 9 meters squared. Doing this calculation will give us 38 electron volts. And finally, for an alpha particle, we use the same equation. H squared over 2m lambda squared. Same thing, except we change the mass to that of an alpha particle. And we end up with 0.005 electron volts. So we see that as we increase the mass of our particle, even at the same wavelength, its energy will go considerably down. And that's it. Thank you very much.